Welcome to the Cross-Cutting Concepts, or the CCC's video. Our goals for this section of the course are to understand the intent of the 7 cross-cutting concepts, to distinguish between them, and to identify examples of the cross-cutting concepts in current curriculum and instruction. This dimension and the identification of these CCCs will be beneficial, as these major conceptual themes may further help to provide equitable learning opportunities for all students. As students become familiar with organizing these concepts that are useful across science content, they may develop additional access points to better transfer this knowledge to new situations, including test items. If students are better able to understand conceptual themes, such as patterns and cause and effect, in explaining science phenomena, then they may be better able to use the pieces of science content they know to bridge their prior knowledge with new material. In addition to referring to this dimension as cross-cutting concepts, sometimes you will hear conceptual themes, unifying concepts, or common themes, to name a few alternative ways to reference these foundational concepts. Here are 2 resources for this section. One is a PDF or hard copy of the framework, and the other is the POW instruction reference document. Before moving on, here is an example of KLS1-1, the NGSS performance expectation we discussed in the last video. Here's the language from the framework to explain this cross-cutting concept. The framework identified 7 cross-cutting concepts, and the code to use for them in this course and in our work is CCC. The cross-cutting concepts are the organizing concepts and ideas that we use to understand science. These are the big ideas that we see in all domains and in all topics. You can see both here and on the reference document. We will go over each of the cross-cutting concepts, but we will only walk through one example in this video. The first cross-cutting concept is that of patterns. A summary statement for the cross-cutting concept of patterns is that observed patterns and nature guide organizations and classification and prompt questions about relationships and causes underlying them. The image that I've chosen to use an example here is the periodic table. I love this example because it's something that was created by scientists who had paid a great deal of attention to patterns and used those patterns to create something that we could use to understand all kinds of things about the world around us. When you're looking at the items and resources, there are 2 key things you might want to look for to identify patterns. Those are repetition and relationships. As many items may have students make sense of and reason about patterns, you will typically see a data chart, a table, or diagram of some sort, but not always. In order to help you become more familiar with the reference document, I want to show you one page of the document here and do a quick walkthrough of how you might use it. As I mentioned in the last slide, we're going to look at times when students are reasoning about a pattern to understand a phenomenon or answer a question. So that when you see an item like this, you might want to head to this page in the reference document and then use the matrix to look for language that's grade appropriate for patterns. Let's think about a potential item you might want to be looking at. Imagine an item that presents a data table that has different cities with some information about each one. Perhaps average temperature and rainfall at different times of the year. Perhaps this question asks students to look at one city on the chart that has unknown temperature and rainfall information and determine what the unknown is based on the patterns seen in the data for the other cities. Let's zoom in on some of the elementary and middle school levels to look at whether it might be appropriate in the grades 3 through 8. If we look at these, is there a statement here that looks or sounds a little bit like the question we were asking our students? That idea of identifying an unknown among cities? I really like the cross-cutting concept statement in grades 6 to 8 where it says, graphs, charts, and images will be used to identify patterns in data. The question we are looking at really asks them to look at the chart and identify a pattern. So I could use this statement for my alignment evidence. I could also use this statement to go directly to the framework and to look at what the authors said. We're not going to walk through a sample like this for each cross-cutting concept, because the structure of the document really remains constant for all subjects. But hopefully this example helps you feel a little more comfortable with using the document. So the second cross-cutting concept is cause and effect, mechanism, and explanation. A summary statement for this one would be that events have causes, sometimes simple, sometimes multifaceted. Deciphering causal relationships and the mechanisms by which they are mediated is a major activity of science and engineering. Cause and effect can sometimes end up being a big umbrella. So much of science relies on the idea of cause and effect. Here are some things you might use as a jumping off point for your alignment. Does it have why statements? Does it have a before and after scenario? What happened? What was the mechanism that made something happen? How can we take our understanding of cause and effect to make accurate predictions. When you see those kind of things happening with the item, it's a good indicator that it might be this cross-cutting concept, but avoid the idea of making everything fit into this statement. Just because cause and effect is so integral to science doesn't mean all alignments should be cause and effect. The third cross-cutting concept is scale, proportion, and quantity. A summary statement for this concept is that considering phenomena is critical to recognize what's relevant at different size, time, and energy scales, and to recognize proportional relationships between different quantities as scales change. There are a lot of times when we call on this in our instruction in order to better understand science. Some things to look for in an item would be measurement, estimation, and conversion. Some guiding checks include how are concepts related by scale and how are they different. This could be found in measures such as time, size, and energy. Also look for systems that may be similar but different in proportion. One thing to be careful of is to remember when you are looking at alignment, if the student answers this item correctly, will it tell us something about their understanding of this concept? Some items might make reference to scale, proportion, or quantity as part of their description or setup, but if students don't need to use the information or reason about it in any way, then it's essentially just background information. So when you're thinking about aligning an item to this cross-cutting concept, be sure to think about whether or not they need to use this concept, or if the information is just being provided as background. The fourth cross-cutting concept is system and system models. A system is an organized group of related objects or component models and can be used for understanding and predicting the behavior of systems. There are many different items that require students to have some understanding of systems or system models. Some key features you might look for in an item are the presence of a subsystem, an interaction, or a closed or open system. Some questions to ponder in your identification include what makes up a system, what is included in a system, what is not included, what type of model can be created to test ideas and to make predictions. Be very critical of what the item asks the student to know before aligning to this cross-cutting concept. The fifth cross-cutting concept is energy and matter, flows, cycles, and conservation. Tracking energy and matter flows into, out of, and within systems helps one understand their system's behavior. Things to try to look for here are cycles, systems, interactions, and conservation of energy or matter. There may be many questions that include energy and matter and don't really ask students to understand this concept. So be careful to look at the degree to which we want to see the movement of energy or matter, not just a static measurement. Once we look at those components of a system, we can start to consider what goes into and out of a system. The sixth cross-cutting concept is structure and function. The way an object is shaped or structured determines many of its properties and functions. Often, biology courses have an entire chapter or unit just about structure and function, but this concept is integral to all areas of science. Think of the structural changes to atoms between elements and the impact that has on the properties of the substance. Or, think about the structure of something like the bridge shown here that determines its function. What are the physical components of something? What are the different roles or jobs of the components? What is it made of, and what do the different parts do? Things to look at are things like the object's shape. If an item asks students to think about the shape of an object, also look at questions that ask students to design or select a structure. Finally, when an item looks at the overall pieces versus component pieces, we are sometimes really looking at structure and function. For example, think of the way different component pieces of the cell perform their jobs based on their structure. Another example is biomimetics. It is the study of structure and function of a biological system as a model for the design and engineering of materials. Also, we could think about biomimicry, which is the approach to innovation that seeks sustainable solutions to human challenges by emulating nature's time-tested patterns and strategies. Let's consider the bio-inspired example of engineering at its finest. This example is the bullet train. The shape of the kingfisher's bill was mimicked by an engineer to create the Japanese bullet train. These engineers used the structure and function principles of the kingfisher as their mentor to solve this unique design challenge. That is, 200 miles per hour traveling train with little to no noise in highly populated areas. The structure they looked at was the beak or the bill of the kingfisher, its behavior for fishing, so its entry into the water, and the function, a soundless, waveless water entry. If you have not explored the Biomimicry Institute, I would suggest you check this out to look at other examples of structure and function and ways to design solutions to human problems. The seventh cross-cutting concept is stability and change for both design and natural systems. Conditions that affect stability and factors that control change are critical elements to consider and understand. Two things to think about when looking at the items for this. First, this is a special case of cause and effect. So if you're looking at an item that you think is cause and effect, you may want to ask yourself whether the cause and effect you're actually seeing is stability and change or vice versa. For example, an ecological system has the introduction of a new species, which initially causes change, and over time, we see stability return to or systematic changes of the species based on this event. This concept might include topics like succession. This is an example of cause and effect, but it also fits into this very specific category of stability and change. Another thing to look for is for questions that prompt students to look at order and disorder. Sometimes these items are drawing on student understandings of stability and change. Our last cross-cutting concept provided a great case of how these cross-cutting concepts can overlap with one another or are reinforced by one another. Cause and effect and stability and change are evidence of how you cannot solely tease one of these things out. This happens elsewhere, and because of this phenomena, you may find it difficult to make single alignment decisions to one cross-cutting concept. And also ask yourself, why are we seeing these overlaps or reinforcements, and what does that also tell us about student understanding?